Thank you, Morgan, and thank you, Neil, for the insightful presentation as well. It sets a wonderful context to the next kind of stage of chapter, which I'm in closing. So what I'm going to cover for the next 10, 15 minutes is what's the need for the resilient infrastructure. And a lot of it is covered, so I will cover that quickly. What's the kind of methodology what we have applied for a particular case study where we have kind of done the entire resilience modeling for the power system infrastructure, which is Antigua and Barbuda, and what are the key indicators what's an utility should look for while doing the planning studies. Now, to give you a little bit of a background, is I think we have well kind of aware of what's the need for resilient infrastructure, and given the complete focus around energy transition, and given the increase in frequency of the climate events as well, it is intrinsic that all the utilities kind of embed the resilient infrastructure risk planning and as well as the entire power system infrastructure planning in their overall capacity expansion modeling itself. So while you plan for your overall generation capacity expansion, while you plan for your transmission expansion system based on the generation expansion modeling and your distribution systems as well, you embed this resilient infrastructure as well through modeling. What's the different risks which are your assets are getting exposed to, and how can you actually mitigate those risks through better planning? So that's the core purpose of it. Now, I'll not get into details about what's the definition of resilience, but what it means is, of course, a deeper and more detailed analysis of the potential risks of these events, and be it's a event caused due to kind of increased heating, or say, for example, wind events or flood events, or say, for example, excessive rains and other things, right? So all these events could actually impact your power systems. So what you do is you try and understand what's the impact of that in all your assets, and then of course accordingly plan your assets to have a better resilient infrastructure. Um, Now, just again getting into a little bit of a theory before I get into the modeling aspects, what we did. So one was so there are three kinds of, again, I would say, the concepts. So one is the disruptive event. Once it occurs, then there is resilience, that your infrastructure comes back to the original position after, of course, getting an impact, and then you have mitigated accordingly. Then there is a degradation, which is, say, for example, in terms of siltation and other things, where your turbines automatically degrade because of this kind of siltation or sedimentation. And third is the collapse, complete blackout scenario, right? So all these three events are sequences of a disruptive event, and therefore you need to plan for all these three, depending on, again, the impact analysis. And as Neil also outlined, we cannot predict the future. Therefore, the only way to do it is range of scenarios. You generate range of scenarios, and then based on those scenarios and as well as a cost feasibility analysis, you invest in those systems so that kind of with a certain probability, you can say that your infrastructure is kind of akin to all these events as well, right? So that's the major purpose of it. So how do you do these or determine these resilience measures and as well as plan for it? So there are very simple four steps again. So first of all, identify the hazards. Based on the hazards, identify the vulnerabilities, and then align the hazards and the vulnerabilities. It could be, again, complementary. Both of the hazards could be coming in together. So you need to understand the impact of these two happening together as well, and then identify resilient solutions, right? So that's the way, very structured approach, I would say any utility should plan. Now, some of these data points, what's required for an utility to kind of capture, and therefore any such planning will require historical data, right? So usually 15, 20 years of data, and hence for an utility, it's immensely important to have a source of this data as well, as a country. And therefore, just outlining that what's the kind of hazards, and based on that, what's the kind of data sources which you will require to again begin your planning exercises. So there could be certain changes in the pattern, which could be peak or seasonal. The peaks could be shifting itself, and therefore the way you have planned your infrastructure could be completely going wrong, right? And this could be very, very, I would say, not so dynamic in that sense. It could be happening very, very slowly, so that you don't understand. So that it's very important that you kind of do a trend analysis, that how your picks are shifting, how your demand is kind of shifting, and all that, and then accordingly kind of start planning for your infrastructure. So that's the first part of it. So therefore you diversify your energy mix and do a adequacy exercise on a regular basis. Most of the Western world have kind of institutionalized a process for doing a resource adequacy exercise on an annual basis, and the utilities kind of do a red filing based on these resource adequacy exercises. So therefore, that's again important that you have a planning exercise on a continuous basis, and it's not a one of 5 year, 10 year kind of a planning, right? So that you can capture the trend and accordingly plan your infrastructure. The second is again, the temperature increases resulting in high mean temperature. I think the last presentation highlighted the various, I would say, risks associated with that. Your substations, your transmission ratings, all of that could actually be vulnerable because of, again, increased temperature. And therefore, again, historically, how has the temperature increased? And that data becomes much more important. And accordingly, again, there were methods highlighted previously as well to capture that and accordingly kind of do a risk rating and take appropriate measures around this. The third is high precipitation and flooding. These are again very, very important for flood prone areas and as well as island nations. So therefore, again, past and forecasted precipitation data, hydrological data to estimate river flows, and flood maps are again very, very important for doing any kind of planning as well. And there are already some of the events which have taken place recently in India. One of the hydro plants got completely submerged through kind of glacial outburst as well. So these are some things which we also need to take care while planning for your assets as well. So you do a generation adequacy, and you certainly kind of come out with a requirement of a hydropower plant, and that could be set up at a location which is completely kind of avoidable. So let's do that. Given the various possibilities of glacial lake outburst and other things. So that's one thing which needs to be again embedded in the planning itself. There are, of course, mitigation measures around that as well. But yeah, I think um, the important point to stress is these are things which needs to be embedded in your planning exercises. High wind speeds, even cyclones and storms, I think this has been very, very frequent these days. Recently, I think in the last couple of years, we've seen several such events coming in, and disruptions occurring in the power infrastructure, especially, as I said, so mostly in the island nations, mostly in the infrastructure facing offshore and otherwise. So we have locations where I think on a repeated basis this has happened over the years. Several cyclones have come and completely infrastructure have been kind of buckled. So for that, what we need is again very, very granular data of maximum wind speed, minimum wind speed, severe and consecutive severe wind days, standard deviations of each of these wind speeds captured over an hourly data map. So all that is required. So for an utility, again, these are some of the data points which you should look at and which you should start kind of capturing it on a systematic basis. That's more important. Of course, there are mitigation measures around undergrounding of lines, cables, or reinforced mounting and other things. But that again requires a lot of investment, and therefore the feasibility needs to be done based on the probability of the impact analysis which the wind is going to impact, right? So therefore, a scientific study on that needs to be done before you kind of plan for investments. Um, Now, we recently concluded a similar study on identifying what's the impact of our grid resilience assessments because of several wind events in the island nation of Antigua and Barbuda. So what we did was, of course, to capture the data from 2000 to 2017 in the islands, and that analysis was done based on that. Then failure probabilities were estimated using historical wind speed data, and then once there are several probabilities assigned, we did, of course, load flow calculation and contingency analysis for the entire network to come out with mitigation measures as well and alternate solutions. So the step one was, of course, to carry out a wind risk analysis. So historically, what we do is a Weibull statistic is used for any kind of risk analysis. So basically, a curve fitting approach was undertaken to on a historical data map to assign probabilities of events. So, say for example, there were wind speeds ranging from, say, on the right hand side, 37 bar to 104 bar, and we ran. And then based on that, certain probability was assigned to each of those, or certain probability of failure was assigned for each of these wind, right? Now, once this is done, based on the Weibull distribution, we kind of came out with a probability of disruption because of the wind speed and the cutoff speed, based on which that above this particular wind speed or above this cutoff speed, there will be certainly a probability of, say, for example, 80% that there could be events or there could be kind of disruptions, right? So once that's determined, the step two was, of course, to do a complete, say, for example, a risk analysis of all the entire infrastructure laid out in the island nation. Now, since we have from the previous analysis, we have a cutoff speed based on which we identify that there is a certain probability or increased probability of an event happening based on that cutoff speed. So what we do is, of course, we assign or we do a Monte Carlo simulations for future analysis. As we said, I think we cannot predict the future, and therefore a range of scenarios of, say, for example, hundreds, thousands, and 10,000s and millions of scenarios were generated for each of those grids using various wind speeds, right? Now, once the wind speeds are varied, say, for example, the mean speed was something around 74 kilometer, and we assigned a probability of, say, 8 kilometer per hour. So therefore, and we generated, again, thousands and millions of scenarios on those wind speeds and assigned those probabilities. So what we found was, after a certain number of simulations, the average unserved energy in each of these grids, because of the events which follows, was remaining more or less equal, right? So that's called the convergence. And therefore, that you take as the average unserved energy in your planning, that this is the maximum because of all the events, whatever could happen, that this is the maximum unserved energy which you will have, or which maximum could happen in that. Now, based on that unserved energy, you try look for solutions and you try to do your feasibility analysis. So in this case, it's just an illustration. So it was happening that after 10,000 kind of scenarios which we generated for different wind speed, it was found that if we run more and more scenarios at 25,000, 50,000, it was converging to a certain ENS number, or energy not served number. And therefore, once we have that, then we know that this is the converged solution which has come. And therefore, that's the maximum energy not served which could happen going forward. And the infrastructure needs to be planned accordingly. Now, once we have done that, then of course the possible solutions were to kind of do a underground network, overhead network interconnections, or new network interconnections, basically to understand the network, what's there, and to try out solutions to do more interconnections. So even if there are outages in one part of the island, then that there could be reduction in the energy not served. So all those solutions were identified, and then that's not the end. Once these solutions are identified, we again do a Monte Carlo simulations and identify that with the new network solutions, then what's the kind of energy not served, which will happen in all the wind speeds again. And when we see that there is a significant reduction on that number, then we conclude that these are possible viable solutions which we could propose. And then, of course, the feasibility analysis based on the energy not served reduction versus the investment is carried out. and that the utility can utilize for their planning, right? So that's what the framework which we used. And again, as I said, so there was like result one, no solutions embedded, and this was the seen as the average unserved energy. And with several new kind of solutions building, we ran the solutions and we saw that how the reduction was happening. And then we did a feasibility analysis of the investments based on the reduction on the unserved energy, right? So that's the framework which we are talking about. But more importantly, as I said, this is the kind of data requirement what's coming in for all your analysis. This has been only kind of outlined for the analysis which we have done. But based on all the analysis which we have just kind of explained, that there could be several events apart from the wind events as well. And there are different data requirements for each of that. So as an utility or responsible utility, you should start capturing all the data so that this analysis gets embedded into your capacity expansion plan.